All right, let's dive right in. We're going to tackle a problem that trips up pretty much everyone. How in the world do you find a real, usable pattern in the total chaos of financial data? So take a look at this. This is Google's daily stock price over a few years. Just try to follow that blue line. It's all over the place, right? It zigs, it zags, it feels completely random. Looking at this, trying to predict what's next, feels like a total shot in the dark. So let me ask you, if you had to put your own money down right now, where's that line going tomorrow? Up? Down? It's a tough one, isn't it? That feeling, that uncertainty, that's the exact problem we're going to unpack today. Now, there's a technical reason this is so hard. The data is what we call non-stationary. That's the key phrase right there. And all it really means is that the basic properties of this data, like its average or its volatility, are changing over time. The rules of the game aren't staying the same. Here's a way to think about it. Stationary data, that's like a calm lake. Yeah, there are little ripples on the surface, but the overall water level, the average, is constant. Now, our Google stock chart, that's a tidal bay. You've got waves, sure, but the whole water level is also rising and falling with the tide. You can't possibly understand the waves until you account for that massive underlying tide. So that's our first job. We've got to deal with the tide. We need to crack the underlying trend before we have any chance of making sense of the day-to-day noise. Okay, so what's the simplest thing we could do? The most obvious first guess? Well, let's just try to draw one straight line right through the middle of it all. This is basically the first thing you'd learn in stats, fitting a simple linear trend. And here's what that idea looks like. We're just making an assumption that underneath all that wild up and down movement, there's a simple, steady upward climb. Seems reasonable, right? But the real question is, does it actually work? Well, to see if our line is any good, we look at the residuals. That's just a fancy word for the leftovers, the data that our straight line didn't explain. And the source material gives it away. It says these leftovers form a V pattern, which is a huge red flag that our model missed something big. And boom, here's the visual proof. These are those leftovers. If our straight line model had worked, this chart should look like random TV static, but it absolutely doesn't. You can clearly see that V-shape. What this tells us, loud and clear, is that our simple approach just failed. The trend is way more complicated than a single straight line. Okay, so the simple approach was a bust. We need to be a little more clever. And this brings us to a really powerful tool for exactly this kind of problem. It's called differencing. The idea behind differencing is actually beautiful in its simplicity. Instead of looking at the stock's price every day, $100, $105, $102, what if we only looked at the change from one day to the next? Did it go up $5, down 3? That single number, that's the first difference. Let's just walk through it real quick. Step 1, you grab today's price. Step 2, you subtract whatever yesterday's price was. And step 3, that little number you're left with, that's your new data point. See what we did? We stopped trying to model the water level and started modeling how much the water rose or fell each day. And just look at what happens. This is the same Google data, but now we're plotting those daily changes. That big sweeping trend, it's gone. Poof. Now the data just bounces around zero. We've completely tamed the tide. We have finally made our data stationary. So now that we have this stable, predictable, stationary data, we can finally open up our toolbox and find the right model to actually describe what's going on. We're going to look at 3 core models. First is white noise. Think of it as pure, unadulterated randomness. Second is a random walk, which actually helps us understand the original, messy data. And third, the star of our show today, the moving average model, which is perfect for the nice, stationary data we just created. So let's start with the most basic ingredient of them all, white noise. Just imagine you're flipping a coin over and over. Each toss is totally independent of the last one. That's white noise. It's the fundamental building block of randomness that we build other, more interesting models on top of. And this is what it looks like in the wild. It's choppy. There's no discernible pattern, and it just kind of hangs out around a stable average. This is what we want our leftovers to look like after we've found a good model. Next up, the random walk. This one's pretty intuitive. Today's price is just yesterday's price plus some random little nudge up or down, a bit of white noise. This creates a kind of memory, which is why it wanders all over the place and creates trends. Sound familiar? Yeah, our original Google stock price looked an awful lot like a random walk. That's why it was non-stationary.
And finally, we get to the moving average model. Now, the name is a little confusing. It has nothing to do with calculating a simple average. What this model really says is that today's value can be affected by random shocks from the last few days. But the absolute most important thing to remember is this. It's a model that is specifically designed to work with stationary data. Okay, the data is prepped. We've got our tools. It is time for the main event. Let's put this all together and see if we can finally actually model what's happening with Google's stock price. So first, let's just see what happens if we try to cheat and skip that differencing step. We're taking our moving average model, the one for stationary data, and throwing it at the original, messy, non-stationary data. The result? Well, look at the orange line. That's our model. It's awful. It completely misses the mark. It's a total failure. But now, look at this. We take the exact same model. We don't change a thing about it. But this time, we apply it to our clean, stationary, differenced data. And suddenly, the orange line, our model, is practically glued to the blue line of the actual data. The fit is just incredibly good.
Let's just put them right next to each other so you can really see it. On the left, you've got a total mess, a model that's completely lost. On the right, you have a near-perfect fit. And what was the only difference? We did the prep work. We made the data stationary first. The difference is literally night and day. This right here is the whole point. Making data stationary isn't just some boring technical step. It's the absolute key to finding the hidden pattern. So think about the journey we just took. We started with a chart that looked like pure chaos. We figured out the core problem, that it was non-stationary, and then we used a really simple trick, differencing, to fix it. And that allowed us to build a model that explains the past almost perfectly. But that leaves us with one last, really important question. Just because we can get this good at explaining the past, what does that really tell us about our ability to predict the future?